picking up good vibrations.
Given a signal x with length capital N, the DFT, discrete Fourier transform, also gives us a signal of length capital N. And this is all we need to recover the original signal. This is good, minimal, but often not enough. Say that we simply want to visualize the discrete time Fourier transform of a given signal. With only n samples, this might be hard, and it becomes much easier if we have more samples. There are many other applications where having more samples makes things easier, or it's even necessary to have more samples. This video explains how to compute more samples through a process called ZeroPadding.
Let us say that we have a signal x of n with length capital N, and let us say that we padded it with capital M zeros, leading to a signal x tilde with length capital N tilde equals capital N plus capital M. The expression for the discrete time Fourier transform of x of n is given on the left-hand side, and the expression for the discrete time Fourier transform of x tilde is given on the right-hand side. Now, for the Fourier transform of x tilde on the right-hand side, we have to take the summation from n equals 0 until capital N tilde minus 1. But since x tilde is 0 from capital N minus 1 until capital N tilde minus 1, we can just sum until capital N minus 1, and there x tilde is equal to x. If we compare the two Fourier transforms, they are exactly the same. Let us now compute the discrete Fourier transforms, which are nothing more than samples of the discrete time Fourier transform. For the original signal x of n, these samples should take place at omega equals 2 pi over capital N k, because its length is capital N. This leads to the expression on the left-hand side. For x tilde, the signal padded with zeros, we have to evaluate the discrete time Fourier transform, which is here denoted by x tilde, for omega equals 2 pi over capital N tilde times k. We could have also denoted the discrete time Fourier transform x tilde by capital X, since we know they are the same. If we write it out, we get the summation from n equals 0 until capital N tilde minus 1 of x tilde times e to the power minus j 2 pi over capital N k times n. Now again, if we use the fact that x tilde is 0 from capital N minus 1 until capital N tilde minus 1, we can change the upper limit to capital N minus 1, and if we use the fact that x tilde is equal to x from n equals 0 until n equals capital N minus 1, we get this expression. This expression is exactly the same as the discrete Fourier transform of the original signal, but capital N is now replaced by capital N tilde, and this should be evaluated from k equals 0 until capital N tilde minus 1, instead of from k equals 0 until capital N minus 1. Thus, we conclude that the discrete Fourier transform of the padded signal corresponds to evaluating the discrete time Fourier transform of the original signal for values of omega equals to 2 pi over capital N tilde times k, where k goes from 0 till capital N tilde minus 1. So we actually get capital N tilde samples in the interval from 0 until 2 pi, and since capital N tilde is larger than capital N, we have a way to evaluate the discrete Fourier transform, discrete time Fourier transform at more samples. Let us illustrate the ZeroPadding procedure with MATLAB. We start by defining an arbitrary signal defined by this vector x, which has components 1, 2, 3, 4, 5, 4, 3, 2, 1. And the way we interpret this signal is by saying that x of 0, the signal at time n equals 0, is equal to the first component of this vector 1, x of 1, which is the signal evaluated at n equals 1, is equal to the second component of this vector, which is 2, and so on. We are going to pad this signal with zeros so that the padded signal has length capital N. Now the original signal has length 10, so if we pick capital N equals 10, we retain the original signal. The padded operation is done here. If we increase capital N, we obtain zeros at the end. Let us plot this, and for now, ignore the two plots that are going to show up on the right-hand side, just focus on the one on the left-hand side. As we increase capital N, we see that indeed the signal is padded with zeros. Let us compute the Fourier transform of the padded signal. For this, we just need the instruction FFT. And then we plot the resulting values of the DFT labeled here by Fx. Since these are in general complex, we need to plot the absolute value or the magnitude and the phase or the angle. Let us see what happens to the absolute value and phase, which are the plots here on the right hand side, as we change capital N. So with capital N equals 10, we have enough samples to recover the original signal x of n. However, it is not a good enough representation to fully characterize the discrete time Fourier transform. In fact, we see that as we increase capital N all the way to 50, we have a much better representation of the discrete time Fourier transform, and we see that it has some oscillatory behavior that was definitely not visible when we made capital N equals 10.